In order for a probability distribution to be valid, two things have to be true. First, all probabilities must be between 0 and 1. Really logically that makes sense. 0 means something happens 0% of the time or never happens. 1 means something happens 100% of the time or always happens. It doesn't make sense that something can happen less than never or more than always. So the first thing we check when we look at a probability distribution to make sure it's valid, are there any probabilities that are negative or greater than 1? So we look at the P of X row, not the X row. These probabilities are all between 0 and 1 for both of the first two examples. The second thing that we know that makes a probability distribution valid is that all of the probabilities when taken in total add up to 1 or 100% of the possibilities. Basically, if we have a fully defined table, we should have 100% of the outcomes accounted for. So for these first two questions, we're really testing that second thing that makes a table valid. We're saying, what would we fill in the blank with in order to make it so that they all added up to 1? So in order to find that, what we're basically doing is taking 1 and subtracting whatever other probabilities we see. So in this case, we know we have 0.1 and 0.8 as probabilities that were already taken. So that means that we have 1 minus 0.1 plus 0.8, which is 1 minus 0.9. That tells me we have 0.1 left over. So in order to make this a valid probability distribution, we're going to fill in the question mark with 0.1. That way, when we add these together, 0.1 plus 0.8 is 0.9, plus 0.1 is 1. All the probabilities add to 1. All the probabilities are between 0 and 1. This is a valid discrete distribution. If I do the same thing for problem 2, again, I'm taking 1 minus all the probabilities added together. In this case, 0.01 plus 0.02 plus 0.03 plus 0.04 plus 0.2 plus 0.1. 0.01 plus 0.02 is 0.03, plus 0.03 is 0.06, plus 0.04 is 0.1. 0.1 plus 0.2 is 0.3, 0.3 plus 0.1 is 0.4. So this really becomes 1 minus 0.4, which gives me 0.6. If I put in 0.6 for the probability of getting 5, now all of these in total do add to 1, so this is a valid probability distribution. Question 3 asks me to find the mean, variance, and standard deviation for the table from question 1. Finding the mean, variance, and standard deviation are similar processes to what we did in the past. The difference is that when we have these tables, these aren't all equally likely events. When I look at this first table that I'm doing, the possibilities are negative 10, 0, and 10. When we were doing probability previously, we said they'd all be equally likely, and really they'd all occur with probability 1/3 or 0.33. Here, when we're doing discrete distributions, they're not all equally likely. This happens 10% of the time, this 80%, this 10%. So when we're trying to calculate the mean, the variance, the standard deviation, things like this, we need to take into account those probabilities instead of dividing by how many equally likely numbers there are. So when I go to find the mean, the way I take into account those probabilities is I take the value, negative 10, which is the first x value you can take on, and I multiply it by the probability of that value occurring 0.1. I then add to that the next value, 0, times the probability of it occurring 0.8, plus the next value, 10, times the probability of it occurring 0.1. So the formula for the mean is x times p of x, all being added together. When I do negative 10 times 0.1, I get negative 1. When I do 0 times 0.8, I get 0. And when I do 10 times 0.1, I get 1. When I add these together, negative 1 plus 0 plus 1 gives me 0. That's a fine mean. Even though we're used to saying that 0 is the absence of something, in this case, the average of these three is 0 because we have a negative 10 and a positive 10 with equal probability, and then we have 0 in the middle. So this is the correct mean of 0. It's also the expected value of the distribution. Expected value and mean are interchangeable here. Expected value just means what on average do you expect to get back from this distribution. So now that we have the mean or the expectation of the distribution, we can use it to calculate the variance. The variance formula is similar to what we've done before. We take whatever the first data point is, we subtract the mean, we square the result. The difference is, instead of just adding together all these squared results and dividing by n minus 1, we need to take into account the probability of them occurring. So we don't worry about any of the division. Instead, we just multiply it by its probability. We're going to add to that 0 minus 0 squared times 0.8. We're going to add to that 10 minus 0 squared times 0.1. So when I do this first one, negative 10 minus 0 gives me negative 10. When I square it, I get 100. Remember that squaring can only give you positive numbers. So if you're squaring negative 10 and getting negative 100, it's because you're not putting the negative inside the parentheses being squared. Here, when I do 0 minus 0, I get 0, which when squared gives me 0. Here, when I do 10 minus 0, I get 10, which when squared gives me 100. So this 100 times 0.1 gives me 10, 0 times 0.8 gives me 0, and this 100 times 0.1 gives me 10. That means the total variance is 20. Again, we don't need to divide by anything because these probabilities did the division for us, basically. They weighted things properly. We don't have to say, let's divide by how many data points we have. If the variance is 20, the standard deviation is just gotten by taking the square root of that variance. If I put the square root of 20 into my calculator, the root of 20 is 4.4721. I'm just going to round to 2 decimals and call it 4.47. You want to make sure that you're doing whatever Cengage instructs you as far as rounding to decimal places. If they don't give you any recommendation, I think in general it'll take something 2 decimal places, but usually it'll say in the instructions how many decimals to go to.